Thanks. I do want to recognize my collaborators on this really quickly, Craig and Ryan and Brad. It's definitely a team effort, so I don't want to take all the credit or all the blame. I will say that this is something we're still working on, though I am very proud of where we've gotten and what we can do and how easy it is to implement these things. So I am very excited to talk to you all about it, even though we're a bit, tapped out from 3 days of conferencing. So the motivating question is, why is neuromorphic not mainstream? And by mainstream, I mean, why is it not in everyone's cell phone, on everyone's desk, cars, drones, et cetera, right? And the sort of quick answer is hardware, but I disagree with that. Right, hardware exists, there's really cool platforms out, and as we've seen over the past few days, hardware is getting better every day, right? There's Loihi, there's Spinnaker 2, Brainscales 2, and so on, and all of these show really nice performance increases, and there's no reason, as an algorithms person, to think that performance increase is gonna stop anytime soon. So instead, what is it? Well, I would argue that the problems are really accessibility, algorithms, and applications. And I think as a community, the NICE community hasn't spent enough time focused on accessibility, right? It's really hard to use a neuromorphic platform, and it's really, really hard to get to do something useful, okay? So if we're gonna try to focus on that, we need to pick an application. I think the application to look at is deep learning. I'm not super pro deep learning. I like it, I think it's cool. I don't think it's the end all be all. But that said, with the amount of interest and research and investment into deep learning, it seems like a good idea to at least talk that language. So let's look at how a deep learning researcher sees the world, okay? If you're coming out of college or grad school, or you're at a startup and you're doing deep learning, you're probably using the stack on the left here, right? You're probably talking at a high level language like TensorFlow or Caffe or Keras, and then that is automatically funneled through usually CUDA onto a hardware platform like an NVIDIA GPU, okay? In contrast, the neuromorphic stack is relatively shallow. You interface with chips using Pine or N2A or CPE. These interfaces are generally platform specific or support one or two platforms. And while there has been some attempt to sort of bridge these two paths, I haven't been really convinced with any of the things available right now. So what we're gonna try to do is slip in here. The project's Whetstone, if you can tell from the title. The idea is we speak the language of the deep learning researcher, we integrate with Keras. We leverage everything that Keras is built off of, including TensorFlow, Theano, CUDA, et cetera. And what we're doing is we're basically tricking all that deep learning stack to give us a spiking neural network out, okay? Once we have the spiking neural network, its weights and connectivities, we can stick that into Pine or N2A, what have you, and then push that onto the hardware that you're interested in. So, the design sort of principles for Whetstone are, first in the first line is it needs to be plug and play, some sort of drop-in mechanism so that somebody who doesn't know what a lift neuron is can still program a spiking neural network for hardware. We want it to be agnostic of the platform. We want it to be compatible with a variety of deep neural network topologies and technologies like dropout, batch norm, et cetera. And we're very interested in not assuming additional resources unnecessarily. So if you look at rate coding or temporal coding, there is an associated time cost. We don't want that. If you look at population coding or neuron doubling, so you have +1, -1, there's an associated space cost. We don't want that. Our sort of mantra is that each node in the artificial neural network is gonna get one neuron in the spiking neural network, and that each layer will correspond to each time step, okay? So here's a quick schematic We have a neural network in the middle, some number of convolution layers, some number of deep layers represented by these blue blocks. The sort of trick of Whetstone is that we start with a traditional artificial neural network. That's represented by the blue colors. And what we do is that during the training process, we switch the activation function from a traditional bounded rectified linear unit or a sigmoid unit slowly to a spiking activation. And that's represented by the blocks turning orange and then yellow, right? So when you see that, that means that layer has become a spiking neural network layer. And you'll see that after a few layers, the spiking accuracy picks up really quickly, essentially matching the non-spiking accuracy, and the loss decreases at roughly the same time. Okay. So that's sort of the idea. The mathematics of it are not deep. The little graph there on the right shows how this works with the sigmoid. You would start off with the regular sigmoid on the far right, then as training goes on, you'd transition towards a spiking network. I will say that since the convergence is non-uniform, this is a very dangerous idea mathematically. We're sort of pulling the rug out from underneath the optimizer, and the shifting energy landscape is something that you should be wary of. But it turns out, as I have on the bottom line there, that if we take a little care and we have a few tricks, it turns out it works out really well in a lot of situations. No guarantees, but it is deep learning, so we don't really have very many guarantees to begin with. So that's sort of the question of how, the question of where and when have been found sort of empirically. The where is easy. We use a bottom-up method. Think about a toothpaste tube, you squeeze from the bottom. That's exactly what we do here. We sharpen the bottom layers first. That allows them to stabilize quickly and allows deeper layers to sort of compensate for any losses that we might have, or at least partially. The when is a little bit more complicated. We started originally trying to hand tune this, but if you think about how many layers you have and start times, end times, and rates of convergence, you realize this is a very large hyperparameter space. So instead what we've done is we've made a adaptive sharpening callback. And what this does is automatically in Keras, every time an epoch completes, it calls a callback. The callback evaluates the loss, looks for stability. If it is stable enough, it will sharpen the layer. If it is starting to lose stability, increase loss, then it'll back off on sharpening it. And so that's pretty much what you need to get started if you're curious about making a Whetstone network. On the right, on the top there, is your standard Keras code. Okay, you start with, say, maybe a dense layer, as an example, a rectified linear activation, a dense output layer, softmax, and then you say go. Okay. In contrast with Whetstone, you define your layer just as you would originally, but then you swap out the activation function for a spiking activation function. Again, this starts out as being a normal activation function. A dense layer. The output, we're using a spiking activation function, which we decode because we can't do softmax and spiking. So we use a spiking network and we decode that to be a softmax during training. And then we attach a adaptive sharpener and click go. Okay? And so what you can see is that there's really not a whole lot to the implementation side, right? There's nothing mentioned about the neuron dynamics or the particular hardware backend. And while the adaptive sharpener is parameterized by, I think it's 2 or 3 parameters, it's largely automatic and you can run with the defaults. So here are some results. If you've seen the poster and seen the demo, you'll know that we have a lot more results now. And in particular, these results were meant to be sort of a grid search of a hyperparameter space. So these are sort of representing typical values, not necessarily the best values that we have. The plot is color-coded. Color represents topology. Blue is the deepest, green is the shallowest. The dot size is the size of the convolutional filter. And we're plotting the spiking accuracy and the non-spiking accuracy. So, perfect replication would be along the diagonal. So the fact that we're pretty close to the diagonal makes us feel good and warm and fuzzy on the inside, but this is MNIST, so it's really not that challenging of a problem. We can go on to other imaging problems like fashion MNIST. For those of you who aren't familiar with this, it has a lot of the same parameters or characteristics as MNIST, the number of samples, the size of the images, its grayscale, et cetera. But it's images of clothing, right? Like jackets, sweaters, and so on. And it's supposed to be more representative of a true computer vision problem. It's a little more difficult, but you see that we have the same sort of performance. We are, again, looking at the relative performance, and you'll see that the deeper networks tend to do better in absolute and better relative when we spike them. Here we have CFAR. Again, the fact that we're following that diagonal is nice, and it shows that we're having a predictable degradation across a scale of topologies, right? So this is a nice indication that we can do sort of a nice job in a lot of different situations, right? Here's CFAR 100, same sort of story. So I think one of the real advantages of going this route is that we can build on all that work and research and investment that's already been put into deep learning, okay? This is true for software, right? We're built onto Keras, which means we automatically get advantages in things like TensorFlow or CUDA. If NVIDIA gives us a new version of CUDA, as soon as TensorFlow supports that, we support that automatically. But we also have things like Python packages. So that means you can do pre-processing or hyperparameter optimization using your whole suite of Python tools without having to go to an external tool, which is a really nice workflow. But we also have the advantages of different deep learning techniques. So for instance, because we're built off of this whole chain of Keras, TensorFlow, CUDA, or Keras, Theano, CUDA, whatever backend you're using, we for free get things like dropout or max pooling, regularizers. All of these are as long as they work during training time, are immediately applicable to our networks. And we can also leverage research in things like optimizers and ensemble methods, again, which will transfer sort of directly. Batch normalization is a great example, and we have a little deep dive into that. So what we're looking at is the right plot is without batch normalization. The red band is the time when we're sharpening the first layer, okay? And if you notice, without batch normalization, there's a huge decrease in accuracy, and it never really recovers from that. In contrast, on the left, you'll notice that the band is much smaller. There's much less loss in terms of the accuracy, and it recovers most of what there is, right? Because batch normalization is already included in everything, we can patch it into our networks without a problem. We adjust the testing parameters at one time, and we don't have to worry about it after that. So it's a really nice way to take work that other people have done and really incorporate that without too much overhead in terms of sweat equity. Another thing that we're really benefiting from is the great work that's going on in optimizers. So adaptive optimizers like Eta Delta and Eta Max do really well in this shifting landscape, right? So the energy minimization problem changes over time, but the adaptive methods are doing a really good job of keeping track of this and still provide consistent convergence. More standard optimizers like Atom, unfortunately, don't do so well, although I should be careful in saying that. Sometimes they do well, sometimes they do poorly. There's a large variability, okay? And because of that variability, we haven't really used them very much. We are at the early stages of doing a sort of whetstone-based optimizer that is aware of this sharpening procedure, which will probably be like an Eta Delta type optimizer that is just aware and modulated by the sharpening rate, okay? But we're not there yet. We have noticed that as this can happen in traditional artificial neural networks, but it also happens in these binarized neural networks, that certain nodes can die, right? Like the neurons can be trained in a way that they never respond to an input. So we found that having redundant output encodings is very helpful. We don't need very many. For something like MNIST or CFAR, we can get away with four-way redundancy, and we get, there's a diminishing returns there, so that's good enough performance. But like I said, those are reflected in the original artificial neural network. So there's still that one-to-one correspondence that we're interested in. And we are working on exploring the space further, but we haven't quite gotten around to it. So the real key is that we're aiming for easy to implement adoption, right? Neuromorphic platforms offer like a really nice promise for swap-constrained environments, whether that's on a drone or in a cell phone or in a car. But the thing is, there's this huge barrier, a barrier of entry, right? You have to know about spiking neurons. You have to know about connectivity. You need to know about how the brain is connected. You need to know dendrites and all these sorts of things. And the problem is that that creates a barrier to adoption, right? So what we're really hoping Whetstone will do is really democratize the availability, or at least the use of these hardware platforms in terms of research lead time, right? It'll make it easier for people to implement real-world networks on these platforms without going through all the hoops and ladders of learning how to use them, is the short, right? So to recap the benefits of these networks, the networks are portable, right? Once they sort of exit the optimizer, it's just weights and connectivities. You can put that into whatever spiking platform you want. We are working on making that process even more streamlined, though we're not there yet. There's a low barrier of entry for the deep learning community. It's based off of standard tools. People are familiar with these in general. We don't require any post hoc analysis. So other methods for training spiking deep networks will train a network up and then analyze it and then create spiking approximations of that based off of rate coding or temporal coding. We don't have to do any after the fact analysis. The network we get out of the training process is the network we can put onto the chips. We try to keep the neuron requirements simple, so we need to integrate and fire a neuron. Strictly speaking, that doesn't necessarily mean they even need to be spiking. We don't need decay or synaptic delays beyond 1. We are looking at ways to incorporate that in perhaps recurrent networks. We haven't done that yet, but I think that's a really interesting direction to go into. Lastly, we have this benefit that we can use a huge library of techniques that the deep learning community has already pioneered and studied extensively, like dropout or batch normalization, which I think this is a point that shouldn't be understated, right? If we read in the next proceedings of NIPS that some new regularizer has come out that does a fantastic job, as soon as the deep learning community has adopted it, Whetstone immediately can benefit from that as well. So that's a really nice way to leverage all that work without having to reinvent the wheel. Okay. I also wanted to mention really quickly this workshop that I'm putting together with Craig Vineyard and Chris Carlson. It's in Brazil in the summer. The idea is not just neuromorphic hardware, but neuromorphic hardware in use, right? So we are interested in taking neuromorphic from the hardware bench and actually putting it to practice. We are accepting abstracts. Please contact me or Craig or Chris or visit the website. I point down there, it's up here. Please visit the website. It's part of IJCNN/WCCI. It should be a lot of fun. And that's all I have for you. So if you have questions for me, I'd appreciate them. Thank you.
Have any questions?
What's your licensing model?
What's your licensing model?
Licensing. So I think we're available for that. You should contact me, send me an email, we'll talk, Yeah. Anything else? No. All right. Thank you, everyone. I appreciate it.